When the barrier potential is slowly varying over the scale of the exponential attenuation length, it is possible to make some analytic approximations. The rigorous analytic approach to such slowly varying potentials is known in quantum mechanics as the WKB method, and that stands for Werner, Kramers, and Brillouin. Here we will derive one important result that is usually obtained from that WKB approach. The standard mathematical approach to this can be found in many quantum mechanics texts. It involves some details of the behavior of particular Bessel functions, actually Airy functions. Rather than repeat that somewhat involved and mathematical derivation here, we will use the transfer matrix to derive this result somewhat informally, though that proper WKB approach is arguably much more rigorous for deriving this result.
So, consider a slowly varying potential of some kind, approximated as a series of steps. So here we have our slowly varying potential. It might have abrupt potential changes at two ends, but within it, we presume the potential is not changing very rapidly. For simplicity, we're going to choose the entering and exiting materials as having the same energy. So we have an instant wave, we'll have a reflected wave, and we'll have some transmitted wave. We presume for some energy E of interest, where we're having E therefore be much less than Vm. So we're well below the top of the barrier here. And we're presuming that we've chosen the layers sufficiently thin, these individual layers sufficiently thin in our calculation, so that at least for interfaces within the structure, the wave vectors for the purposes of the boundary condition calculation are approximately the same on both sides. Then for interfaces within the structure, the boundary condition matrix will become approximately a matrix that is just the identity matrix, because this delta M here will just be approximately 1. So roughly speaking, this will look like an identity matrix. So this part of my derivation here, my informal derivation, is indeed a little bit approximate and not very rigorous. As I said, you can look in textbooks to find the rigorous and proper WKB derivation. I'm just sort of justifying it informally here. So with internal boundary condition matrices therefore approximated by identity matrices, we simply omit them here. So the transfer matrix becomes this product here, but missing all the boundary condition matrices between the propagation matrices. But we have left in the boundary condition matrices at the beginning and end of the structure. And that's because the potential may be quite discontinuous there, as I showed in my original diagram. Well, the product of two diagonal matrices is simply a diagonal matrix whose elements are the products of the corresponding diagonal elements. That's easy to check by multiplying these two matrices, for example. So, since the propagation matrices are all diagonal, and previously we showed them to be of this specific form, then the product of all of them is just in this form here, where G is simply the product of these exponential factors for each layer, which will, in this case, turn out to be exponentially decaying factors in this product here. The k's will turn out to be imaginary. Now, if we've chosen the layers to be sufficiently thin, we may take the summation to be approximately equal to an integral. So this sum over all of these kappa q's times dq's will just turn into an integral over the total thickness of our barrier here of kappa of z dz. And if we're taking our structure to start on the left at z equals 0, then this z total will just be zn plus 1, the position of that interface. Hence, this g factor here, the exponential of this integral here will just turn out to be the exponential of this integral, where v of z is the potential as a function of position z. With our first and last boundary condition matrices in this form, then our total transfer matrix, multiplying everything together, would be something that looks like this. So with that matrix, multiplying out these two matrices gives us something in this form. We remember that we are particularly interested in T11, because that is going to give us our transmission, actually, in this case. And T11 is the product of this column into this row here, so we get this result for T11. Since the barrier is presumed thick, this factor here is presumably small, so T11, which would be everything we wrote down before, we can approximate it as this expression here. This term is going to dominate entirely, and this term is going to be relatively negligible. So from our transfer matrix, on the presumption there's only a wave leaving to the right, that means that the incident wave amplitude, relatively speaking, is T11 times f. And so the transmission, which we can now think of as mod f squared over mod a squared, because we chose the incident and exiting layers to be of the same potential, will just be 1 over modulus squared of T11. So finally, we would obtain in this simple model and this somewhat informal derivation here that the transmission coefficient, the probability of an electron passing through this barrier, is this prefactor here times this exponential here. We've got a factor of 2 here because we have to square this up, the T11. So in the exponential, we get a 2. So this is a simple derivation of a penetration factor for slowly varying barriers. As I said, it's better to do this more rigorously using the full WKB approach, but you end up with the same answer here as we derived a little bit informally with this derivation related to the transfer matrix. So in this frequently used expression for tunneling probability, or so-called penetration factor, the prefactor contains the input and output boundary conditions, and the exponential approximately expresses the penetration within the barrier.